Welcome back, folks. Greg Silverman here, CIO and bow ties. Another session of Come Learn with me. But first of all, this is a South African flag painted on top of a building. I think it's in Johannesburg. I'm not quite sure, but that is just paying my respects to my beloved South Africa. And I hope you guys are all safe and well with the new strain, new variant coming out. And I hope everything gets squashed pretty quickly. My heart goes out to you, and you're in my thoughts. Okay, another session. Come learn with me with Greg Silverman, your Chief Investment Officer for the minute. If you want to hear more about our investment side of our business, follow this URL. Not yet, only at the end of the video. You have to stick with us. And we'll tell you more about our investment function. So please take a look at that. Okay, this article, let's put it into our Come Learn with Me uranium section. That's a pretty cool picture, right? And this is about new tech promises to enable the ultimate nuclear power. I've been telling you guys about this for a while. We've been looking at investments in this space. It's not your 1950s nuclear program anymore. Nuclear fusion, the super clean high energy power source of the future, is nearly here. On-tap nuclear energy with no radioactive waste, all powered by the most abundant element in the universe, fusion. This has long been the holy grail, as it would revolutionize our lives and turn the tides on climate change. But this era-defining technology is an engineering nightmare. It turns out to be near impossible to make what is essentially a miniature sun, let alone get any energy from it. But a recent technological development could change this, bringing us closer to a usable fusion reactor, and in doing so, ushering in a new age of clean, limitless energy. Before we dive into the new development, how does fusion work and why could it be so revolutionary? There are two types of nuclear reaction, fission and fusion. Fission is a chain reaction of splitting atoms. This is what powers our current nuclear reactors. While it's very clean and safe, in fact, nuclear fission power is still the cleanest and safest form of power that we have right now. It produces some nasty radioactive byproducts that are hard to dispose of, and there is limited supply of material that will fission, i.e. uranium. Fission, okay. Fusion, on the other hand, forces two atoms together to become one. This is what powers our sun. Deep in its core, the temperature and pressures are high enough to force hydrogen atoms together, fusing them into helium, and in the process release a lot of energy. Fusion is by far the most energy-dense power source. For comparison, a kilogram of coal contains around 230 megajoules of energy in the form of combustion. A kilogram of uranium-235 contains about 86,400,000 megajoules of energy in the form of fission, but a kilogram of hydrogen contains 845 million megajoules in the form of fusion. This means that a single kilogram of hydrogen can power the average house, 10.399 kilowatts or 37.44 megajoules per year, for 22,569,444.4 years. Don't forget the point, or enough energy to power all of Spain's home for a year with a few million megajoules spare. Spain. The Costa del Sol. Fusion would be by far the most eco-friendly power source. It uses tiny amounts of fuel to make huge power. The only waste product is helium, and the power plants could create vast amounts of energy from a tiny site. There would be no carbon emitted, no extensive land use like solar and wind, no dangerous waste products, and very abundant fuel supply. Fusion really could revolutionize humanity and bring in a new era of clean energy. But there is a catch with fusion that fission doesn't have. Uranium will fission all by itself. The trick is controlling it so that it doesn't burn through its energy too quickly. This means we don't need to put any energy in to get the energy out of uranium. On the other hand, fusion takes insanely high temperatures and pressures to get the hydrogens to fuse into helium and release their energy. In the core of the sun, gravity does all the work, enabling fusion to happen spontaneously. But here on Earth, we need to expand vast amounts of energy to create the same conditions. Well, look at that. Inside the tokamak reactor. Oh, we read about this a while ago. Check out some of our previous uranium articles. We read about the tokamak. We have had machines that can create such conditions for decades. Two examples are the infamous tokamak and the National Ignition Facility, NIF. Tokamak uses powerful magnets to squeeze and heat the hydrogen in a donut-shaped reactor design known as magnetic confinement refinement. In contrast, NIF uses powerful lasers to ignite a minuscule pellet of hydrogen, a reactor design known as an inertial confinement reactor. But these machines have one crucial problem. They use more energy to fuse hydrogen than they can extract from the fusion. This is the key to unlocking this revolutionary power source, creating a machine efficient enough to get a net gain in energy. Currently, the NIF's internal confinement reactor, ICR, holds the record as the most efficient. In August 2021, NIF managed to extract 70% of the energy from a single fusion reaction, beating their old 2018 record by a factor of 8. Wow. Getting there. With ICRs, there are 3 areas you can gain efficiency: the laser, the pellet design, and the energy extraction. Recently, scientists have made considerable strides in pellet design and energy extraction. Computer simulations and new materials have led to pellet designs that compress and heat the hydrogen within them much more evenly than before, leading to efficient and complete fusion. Fusion emits most of its energy in the form of fast-moving neutrons, so scientists have developed lithium blanks that can capture these particles, heating the blanket up, which can then be used to drive a steam turbine. We already use hyper-efficient steam turbines for fossil fuel plants and fission plants. This technology is very mature and has little room to improve. NIF target assembly holds hydrogen pellets. These advances are what led NIF to an incredible 70% yield just a few months ago. Let's just capture this in the data banks. However, the facility hasn't any major laser updates in a long time. This means one of the most significant opportunities to increase efficiency in fusion reactors is the lasers. This is where a recent project could make NIF's lasers so efficient that they could be the first to achieve the monumental milestone of a net energy gain. This is interesting, huh? NIF uses a high-powered infrared laser and a series of complex optics to convert the beam into a much higher frequency ultraviolet light that forces the hydrogen to fuse. Let's read that again. NIF uses a high-powered infrared laser and series of complex optics to convert the beam into a much higher frequency ultraviolet light that forces the hydrogen to fuse. It was built this way as infrared lasers are far more efficient than ultraviolet lasers. So even though the laser would lose a little energy in the optics, it was still the most efficient method of generating the insanely intense ultraviolet lasers needed for fusion. It's the flux capacitor. Just kidding. Power amplifier. Transport spatial filter. Optics. Fine. But a new type of laser. Let's see. Let's get a picture quick. Well, that's the laser. Viewing portal info NIF's reactor. Wow. I don't know if I want to be that close to a reactor when it's undergoing nuclear fusion. But a new type of laser could change this. Recent research into argon fluoride lasers shows that they could be even more efficient than our current infrared lasers, as the AfLs emit deep ultraviolet, so don't need any optics either. The US Naval Research Laboratory has announced that they will be designing AfLs specifically for ICRs, promising a 100-fold increase in efficiency. If they achieve this goal, then the next generation of ICRs will achieve a net energy gain in energy. That's, go read Ayn Rand. That's the basis of the book. What's it called? Atlas Shrugged. Could this be enough? This might be enough to get a usable fusion reactor. AfLs could tip the yield past 100%, but not significantly past that mark. This means that yes, they can produce energy, but only a minuscule amount, as ICRs are extremely expensive. This low energy output will stop them from being commercially viable. Damn, so close. Okay, more leaps in efficiency will need to happen to get the push the yield well past 100% and closer to 150 or 200% mark, enough to power the next fusion and still extract a large amount of energy. But even then, these reactors need to become incredibly reliable. ICRs ignite one pellet at a time, so you need to fire it billions of times over its lifetime to have a commercial reactor, something our current technology can't achieve. But it seems these advances are coming soon. The leap forward in efficiency and reliability over the past decade have been astonishing. If this trend continues, you may see an ICR capable of commercial power by the end of the decade. Novel reactors designs such as TAE's boron accelerator promise to outstrip ICRs in the coming years. So it might be possible to get several usable fusion reactors designed by 2030. These innovations couldn't come at a better time. The Earth is groaning under the weight of our carbon footprint. Solar and wind technology can't power us without damaging the environment. There are plenty of political problems powering the world with fission power. Make no mistake, a functioning fusion reactor would turn the tides on climate change. Okay, a little bit of that. Just want to make sure we get a balanced article. All right, guys, very interesting. We're actively investing in the uranium space, so nuclear fission, I guess. We're not buying hydrogen right now, although we should be looking at it, right? Anyway, we're actively investing there, looking at opportunities. If you'd like to take part more in the investment side of our business, hop over to this URL. You can read more about me, philosophy, process, and see some of the opportunities that we are featuring on the investment side. So guys, come on over, check us out. If you like these articles, please subscribe and like, and subscribe to YouTube and like. You got it. All right, Greg Silverman out for now.